Alright, so we are about to do the back side of the Using Fundamental Theorem of Calculus 3 notes, and we'll start with sort of a big picture review of what we just figured out on the front side. So the Fundamental Theorem of Calculus is looking at integrals, and we started describing integrals. We're looking for an integral from point A to B of some function with respect to x. We started introducing integrals as the area between the curve and the x-axis. It was a question about finding area. And as we've been working with integrals, we've come to see that you can look at that question in a different way, and in the front side of these notes what we came to see is that if you know the rate of change of some function, right, so if we know the derivative of some function, well then we can use that to figure out how much the function itself is changing over a given interval. So it's a different way of describing what the fundamental theorem of calculus is doing. So here I know the derivative of a function, and that allows me to figure out how much the function is changing over a particular interval. And here I'm using the interval from A to B. Right? So the integral, instead of being looked at as a measure of area, the integral is a measure of the change in a particular function, in this case f of x. All right? So example 3. We're going to make a couple of changes here to the text, given that chances are that as you're watching these video notes, it is a snowy day in Brookline. And so in this, it's not the latest storm, it's the current storm. In this storm, snow is falling at a rate of square root of t. And here we're measuring x in hours since the start of this storm, and given the robocall that I just received from the town of Brookline saying that there was going to be a snow emergency starting at 6 o'clock Wednesday morning, then we could say that x equals 0 is defined as 6 o'clock in the morning Wednesday morning. So question A, we're going to figure out how much snow fell in the first 9 hours of the storm, which I want you to use your calculator to do that. The integral then we're looking at is from the start of the storm, 0, to 9 hours later. And I'm going to write the function using exponent notation. Right? So we're looking at that function, square root of t with respect to t, and if you do this on your calculator, put t, the square root of t, or t raised to the 1/2 power, into y1, and then do second calc and calculate the integral. You will find that you get an answer of 18 inches. Right? So in the first 9 hours of the storm, 18 inches of snow fell. All right, so now here's the question that gets us back to this sort of moral, the context that we're looking at this. So we know in the first 9 hours of the storm, 18 inches of snow fell. So then the question is, how come this is not necessarily the amount of snow that is on the ground after 9 hours? And if you just think about what's going on, the answer is pretty straightforward. because there may have been snow already on the ground. Which is to say, we don't know at, what are we calling this function? We'll call this function f. We don't know how much snow there was at 6 o'clock in the morning on Wednesday morning. All right? But if we know, actually, let's do this. Let's not call this function f. Let's call this function s for snow. So if we know that at the end of 9 hours, there is 2 feet of snow, or in other words, 24 inches of snow, then it's a pretty straightforward thing to figure out how much snow there must have been on the ground at s equals 0, right? Because by the fundamental theorem of calculus, we look at the integral from 0 to 9 of our function. We don't want to actually. We're going to call this the derivative, right? Because we know that the snow is falling at a rate of the square root of t. So this is the derivative of the function, and by the fundamental theorem of calculus, we know that that means that if we take the amount of snow we have after 9 hours and subtract the amount of snow that we had after 0 hours in the storm, then that'll give us the total amount of snow, that fell. So that's going to be 18, and we're told that this is 24, and we're looking for where it was at the start, and we know that at the end there was 18 inches of snow total. So pretty straightforward to see that there must have been 6 inches of snow on the ground when the storm started. All right, example 4, and then we're done with the notes. So example 4, instead of giving you a function, what you've been given is the graph of the function. Well, and actually it's not even the graph of the function. What you've been given is the graph of the derivative of the function. So this right here is the derivative of the function with respect to x. And if we're trying to find out what f of 8 is, so f of 8 would be, so this is the derivative function, and we want to know after 8 seconds, whatever units we're using, what the value of f is, but this is the derivative function. So in order to do this, first thing we want to compute is we want to compute the derivative from the starting point that we know, which is 2, up to our end point, which is 8. Find the integral of that. I think I said derivative before, I meant to say integral. So we want to find this integral right here. We're going to do this graphically. And let's see. So we are going from 2 to 3, we're starting at 2, so between 2 and 4, if we just simply read the area off of the graph, this area in here ends up being a total of 3 units, and then we have the area that's underneath the graph, from 4, oops, wrong side, from 4 out to 8. So we have this area here. That total area, if you count up the boxes in there, that total area ends up being 12. Can't quite read that, can you? Here, let me do that for you. So this area in here, oops, clean this up. Give me 1 second. Talk amongst yourselves while I fix this up. All right, so this area is 12. So what we know then is that back here to our integral, using the fundamental theorem of calculus, the starting position, the ending position minus the starting position is going to be the total that we have. So the ending position, f of 8, minus the starting position, f of 2, well, that's going to be equal to the integral. Well, the integral is 3 units of area up on the top, 12 units of area on the bottom, which then means that the value of the integral is going to be -9. And then we know we're looking for f of 8. We know that f of 2 is 15, and we know the value of the integral is -9, which means that f of 8 is equal to 6. And then the last question here, if we were going to go and do this by finding the formula, right? So A was us finding f of 8 using the integral, the value of the integral, -9. So in B, we're going to do it, if you will, algebraically. So the first thing is we figure out what the equation for this line is, right? So the line is the derivative of x, and it goes through the y-axis at 6, and it's got a slope, rise 3, we go backwards 2, so it's got a slope of -3/2. So the equation for that line is -3/2 x plus 6, which then means that the f of x would be the antiderivative of that, which would be -3/4 times x squared plus 6x plus some value of c. And then we plug in what we know here. So if we're looking for f of 2, if we know f of 2 and f of 2 is 15, well then that means that 15 must be equal to -3/4 times 2 squared plus 6 times 2 plus c, and then in solving this we can figure out that c must be 6. And then if c is 6, then we have our equation, right? So our function f of x is -3/4 x squared plus 6x plus 6. And now if we're looking for another color here, if we're looking for the value of this function at 2, well then we just plug it into this equation that we've just built, -3/4 times 2 squared plus 6 times 2 plus 6, and we evaluate all of this. And, oops, sorry, I'm not plugging in 2. I'm plugging in 8. So that should be 8, that should be 8, that should be 8. And then the conclusion, f of 8 is equal to, we evaluate all of this and we find out that f of 8 is 6. All right. We're done. Before I go though, I just want to point out it is a coincidence that the value of C and the value of f of 8 are identical. And the reason for that, if you were to take and graph this function that we just figured out, the function looks like this. It's a parabola. And at 0, this point right there is 6, and at 8, if you go out to where x is equal to 8, then the value of the function is the same. So at 0, you get c is 6, and at 8, you also get c is 6. And it just is a coincidence that those two are the same. And we are now done with the notes.